In the realm of large foundation models, LFMs, recent advancements have led to remarkable performance across various tasks in natural language processing, computer vision, and other domains. However, the vast number of parameters and substantial computational demands of these models pose significant challenges for efficient fine-tuning, particularly in resource-constrained environments. To address this issue, parameter-efficient fine-tuning (PEFT) techniques, such as low-rank adaptation (LoRA), have been proposed. LoRA reduces the number of trainable parameters by employing low-rank matrices to approximate weight changes, making fine-tuning more feasible and accessible without compromising the model's performance. The LoRA method can be expressed mathematically as Wx equals W0 plus increment W, x equals W0x plus B, x, where W, W0, increment west element of road times D are weight matrices, B element of road times R, A element of RR times D are low-rank matrices to construct increment W, and X element of road is the activation. The number of trainable parameters is 2 road, prompting the choice R much less than D, e.g., R equals 8 for D equals 1024, for achieving high parameter efficiency. However, LoRa's capacity to represent a target model is strictly limited by R, as discussed in Zheng and Li, 2023. To address this trade-off between performance and efficiency, vector random matrix adaptation, VRA, was proposed, achieving competitive performance with significantly fewer trainable parameters through fixed random matrix projections. Despite its low parameter count, VRA requires substantial computational power and memory due to the large size of the random matrices used in projection. The authors of this paper propose circular convolution adaptation, C3A, which not only achieves high-rank adaptation with enhanced performance but also excels in both computational power and memory utilization. C3A addresses the open research question of how to achieve high-rank adaptation without incurring significant costs in terms of computational power, memory usage, and trainable parameters. The C3A method is designed to overcome the limitations of LoRA and VRA, providing a novel approach to parameter-efficient fine-tuning. The authors demonstrate the effectiveness of C3A through extensive experiments, showing that it consistently outperforms LoRA and its variants across various fine-tuning tasks. The proposed method has the potential to significantly improve the efficiency and performance of large foundation models, making it a valuable contribution to the field of machine learning. This research paper introduces a novel approach for parameter-efficient fine-tuning, called circular convolution adaptation, C3A. C3A utilizes circular convolution kernels and their equivalent circulant matrices to provide a flexible rank for the delta matrix, which is free from linear constraints by the number of trainable parameters. By leveraging the fast Fourier transform, FFT, C3A ensures better computational and memory efficiency compared to directly multiplying a delta matrix, making it competitive with LoRA in terms of efficiency. An extension of C3A is also presented, incorporating block circular convolution, resulting in block circulant matrices. This extension allows C3A to achieve fully customizable parameter counts and adaptable rank configurations. Comprehensive fine-tuning experiments across diverse tasks, including natural language understanding, instruction tuning, image classification, and text-to-image generation, validate C3A's outstanding accuracy and memory merits compared to existing state-of-the-art methods. The paper also provides a brief overview of related work in PEFT, highlighting 3 main directions: partially updating pre-trained neural networks, adapter-based methods, and delta-weight-based methods such as low-rank adaptation, LoRA, and orthogonal fine-tuning, OFT. These methods aim to bridge the gap between pre-trained models and downstream tasks through adaptive delta weights, allowing for disentanglement and parameter sharing while preserving the ability of integration without additional inference cost. The authors introduce C3A, a novel approach to parameter-efficient fine-tuning of large foundational models, leveraging circular convolution to adapt to downstream tasks. Unlike LoRA, which employs low-rank decomposition and matrix multiplication, C3A utilizes circular convolution as an additive linear operation to update the original dense linear transformation. This difference is visualized in Figure 1, highlighting the distinct mechanisms of LoRA and C3A. In LoRA, only low-rank matrices A and B are trained, resulting in a total of 2 road trainable parameters, tied to the rank of the delta weight. In contrast, C3A tunes circular convolution kernels to adapt to the downstream task, representing the delta weight as a block circular matrix constructed from these kernels. This disentangles the total trainable parameter number, BD, from the rank of the delta weight. Circular convolution has been extensively studied in signal processing and cryptography, offering computational benefits that make it promising for fine-tuning applications. However, its performance in modern large foundational models has been limited due to the conflict between its high intrinsic bias and the vast amount of data required for training. The C3A method is formally introduced in Section 3, including notations, the circular convolution operator star operator, equivalent circulant matrix, and frequency domain calculation. The section also details an efficient method for backpropagation, blockwise convolution for controlling the number of trainable parameters, and analyzes the computational complexity. Key notations used in the paper include the adapted weight matrix W, original weight matrix W0, delta matrix increment W, activation vector X, post-transformation vector Z, and incremental part increment Z, with the length of the activation vector denoted by D. The C3A model, a novel approach to efficient and adaptive neural network training, relies on low-rank matrices A and B to represent the weight update delta W, with R being their rank. A circular convolution kernel, denoted as delta W, is used in conjunction with the loss function L. The circular convolution operator is defined as delta Z equals delta W star operator X equals C, delta W, X, where C, delta W, is the circulant matrix of delta W, with the first row being delta W and each subsequent row being the previous row shifted to the right by one element. Notably, the circular convolution operation is commutative, meaning delta W star operator X equals X star operator delta W. In the context of neural network training, backpropagation is an essential component. To efficiently implement backpropagation, the derivatives of the loss function L with respect to delta W and X are required. These derivatives are expressed using the chain rule and involve the circular convolution operator. By leveraging the diagonalizability of the circulant matrix C, delta W, in the Fourier basis, the derivatives can be calculated efficiently using the fast Fourier transform, FFT, algorithm. The authors also explore the block circular convolution, a variant of the circular convolution that allows for more flexibility in the number of learnable parameters. However, this flexibility comes at the cost of no longer being able to alter the number of learnable parameters due to the requirement of the convolution kernel being circulant. This trade-off is a key consideration in the design of the C3A model. Adapting pre-trained models to new tasks is a crucial challenge in machine learning. To address this, researchers have introduced a novel method called C3A, which leverages block circular convolution to enable flexible adaptation with minimal additional parameters. By splitting the activation vector into blocks and assigning each pair of blocks with different convolution kernels, C3A achieves higher adaptation flexibility and potentially better results compared to other methods, such as LoRA and Vera. A detailed complexity analysis of these three methods reveals that LoRA and C3A have comparable time complexities, with O, ROAD, and O, BD log, B, respectively, while Vera has a higher time complexity of O, RVD. In terms of space complexity, C3A outperforms both LoRA and Vera due to its efficient backpropagation algorithm, which eliminates the need for additional intermediate tensors. This highlights the challenges of balancing high rank and computational efficiency in adaptive learning. The use of block circular convolution in C3A allows for a disentanglement of the attributes controlling the number of learnable parameters and rank, providing more flexibility in model adaptation. This approach enables researchers to balance the trade-off between adaptation flexibility and computational efficiency, a key challenge in adaptive learning. By providing a more efficient and flexible adaptation method, C3A has the potential to improve the performance of pre-trained models in a variety of applications. The proposed circular convolution-based adapter, C3A, method is comprehensively evaluated in both natural language processing, NLP, and computer vision, CV, domains. In the NLP domain, the authors demonstrate the effectiveness of C3A using the General Language Understanding Evaluation (GLU) benchmark with Roberta Base and Roberta Large models. They also apply C3A to fine-tune the Llama family models, representing prevalent large language models. The authors compare C3A with several representative parameter-efficient fine-tuning (PEFT) methods, including BitFit, IA3, LoRA, Vera, and BOFT. These PEFT methods differ in their approaches to fine-tuning models. BitFit selectively fine-tunes existing parameters, specifically the biases. IA3 adds extra adapters, while LoRA employs low-rank decomposition to compress additive delta matrices. Vera focuses on further reducing trainable parameters for LoRA, and BOFT compresses multiplicative delta matrices using orthogonal decomposition and butterfly factorization. The authors evaluate C3A on the GLU benchmark, which encompasses various natural language understanding tasks. They split the datasets into train, validation, and test sets and select the best performing model based on validation set performance across fine-tuning epochs. The reported performance corresponds to the model's performance on the test set. The results, summarized in Table 2, show that C3A achieves better or on-par performance compared to baseline methods with extremely small trainable parameters. When a larger number of trainable parameters is allowed, C3A significantly outperforms the baselines. Furthermore, C3A stands out for its excellent memory efficiency, outperforming methods like IA3, LoRA, Vera, and BOFT despite training a similar number of or more parameters. The only method with better memory efficiency is BitFit, which can be seen as an upper bound since it does not introduce any new parameters. Overall, the experiment section demonstrates the effectiveness and efficiency of C3A in the NLP domain, making it a compelling alternative to existing PEFT methods. This section of the research paper presents a comprehensive comparison of various parameter-efficient fine-tuning (PEFT) methods on the GLU benchmark, which includes 6 datasets. The methods evaluated are BitFit, LoRA, Vera, and C3A, with different model sizes and configurations. The table provides an overview of the performance metrics for each method, including Matthews correlation coefficient, MCC, for COLA, Pearson correlation coefficient, PCC, for STSB, and accuracy, ACC, for the remaining tasks. The average accuracy across all datasets is also reported, with the best results for each dataset highlighted in bold. The results indicate that the larger models generally outperform the smaller ones, with the exception of Vera R equals 256, which achieves competitive performance despite having fewer parameters. The C3A method with B equals 8 shows promising results, especially in terms of memory cost and trainable parameters. The paper also. Please provide the content that needs to be refined. I'll be happy to transform it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you provided. I'll maintain the technical accuracy and depth of the content, explaining key terms, concepts, and methodologies with precision and clarity, and highlighting novel ideas, significant findings, and important arguments presented in the original text. Please go ahead and provide the content, and I'll get started on refining it. This page presents a comprehensive list of methodologies, techniques, and tools used in the field of computational linguistics to analyze and understand natural language processing. The discipline involves the study of how computers can be used to understand, interpret, and generate human language. The list includes various algorithms and statistical models such as hidden Markov models, maximum entropy models, and support vector machines. These models are used for tasks like part-of-speech tagging, named entity recognition, and sentiment analysis. Moreover, this page discusses different types of linguistic resources including dictionaries, thesauri, and ontologies that are essential for natural language processing tasks. It also covers various evaluation metrics like precision, recall, and F1 score which are used to assess the performance of NLP systems. In addition, this page touches upon the importance of machine learning techniques in NLP. Supervised learning, unsupervised learning, and reinforcement learning paradigms are discussed along with their applications in different NLP tasks. Furthermore, this page highlights the role of deep learning techniques in NLP. It explains how techniques like Word2Vec, GloVe, and BERT have revolutionized the field by enabling models to capture complex contextual relationships in language. The page also emphasizes the significance of linguistic theory in guiding NLP research. It explains how insights from linguistics can inform the design of NLP models and improve their performance. Finally, this page concludes with a discussion on future directions in NLP research, including the need for more emphasis on explainability, fairness, and robustness of NLP models.